Greetings, students. This is Mr. Allen. Today's lesson is on section 1.5, infinite limits. Our objectives today are to determine infinite limits from the left and from the right, and to be able to sketch the vertical asymptotes of the graph of a function. So this is actually a pretty easy lesson, I think, but we do kind of need to wrap our head around this infinity thing. So consider the function that I have here at the top, f of x equals 3 over x minus 2. Says from the figure, so I've got the graph down here below on the right. So here's our graph down here. And we can see that it looks similar to that main function that we're used to, 1 over x. And we can see that this function decreases without bound as x approaches 2 from the left. So as we come in from the left, it is going to decrease without bound. Now as we approach 2 from the right, it actually increases without bound. If we were to look numerically, now that's just graphically, if we were to look numerically, again, we're interested at 2, we can see that the y values as we get closer and closer to 2 are getting larger and larger negative. If we approach 2 from the right, they are getting larger and larger positive. This behavior is denoted as the following. Here's how we would write it symbolically. The limit as x goes to 2 with a negative symbol, remember that means 2 from the left, equals negative infinity. And the limit of the function as x goes to 2 from the right, that's what the little plus symbol means, that is equal to positive infinity. In other words, we're going to use negative infinity when it decreases without bound, and we're going to use positive infinity when it increases without bound. A limit which f of x increases or decreases without bound is called an infinite limit. Now, this is a very challenging looking definition, but here's basically what you need to know. The definition of an infinite limit. Let f be a function that is defined in every real number in some interval containing, except possibly containing c itself. Then the statement, the limit as x approaches c equals infinity, means that for every uppercase M greater than 0, there exists a delta greater than 0, such that f of x is greater than m whenever 0 less than absolute value of x minus c is less than delta. So this is the delta definition, delta epsilon definition for an infinite limit. You really don't need to worry too much about this, but I'm just including it if you are concerned about the how rigorous this class could be. By the way, this is the definition down here is for the limit going to negative, being negative infinity. Okay, let's go ahead and go to the next slide. So example 1 here, I've actually got 2 parts. I've got A and B. It says determine the limit of each function shown in figure 1.3 as x approaches 1 from the left and from the right. So both of these functions have kind of different things going on. Our first function here is 1 over x minus 1 quantity squared, and our second function here, g of x, is negative 1 over x minus 1. Notice that each of these graphs have asymptotes, vertical asymptotes at x equals 1. So let's look at the algebraic solution of the first example. If you remember, the denominator of the first function, the f function, is the quantity x minus 1 squared. Now, as x approaches 1 from the left, so if I've got a number that's less than 1, this is going to be a positive small number. So if I had put in 0.9, that'd be 0.9 minus 1, which is negative 0.1 squared, which is a small positive number. Thus, the quotient is going to be a large positive number, and the reason is on the top you have a constant 1, and on the bottom we have a smaller number. As I get closer to 1, that bottom number, which is positive, is going to get smaller and smaller and smaller. The top's still saying 1, so it's actually going to grow. And it's going to grow and approach infinity. In other words, it's going to grow without bound. So we can conclude that the limit of the function as x goes to 1 is infinity. And it actually applies to both sides. If I came in from the right side of 1, I'm still going to get a small positive number, and a positive divided by a positive is positive. So now let's look at example B. Example B, we're still approaching 1. Now the denominator here is x minus 1. This is going to give us a small negative number. So if I've got a number that's less than 1, so let's say it's 0.9, I'm going to take 0.9 minus 1, which is a small negative number. Now the top, by the way, this is going to produce a small negative number. The top is already a negative number. So as I come in from the left, I'm going to get a negative number over a smaller negative number, and the denominator is getting smaller and smaller. So that's a negative over a negative, which is a positive, so it's going to go to positive infinity or infinity. So that's what this limit says here. The limit of the function as x goes to 1 from the left is positive infinity. When we come in from the right, so if I get a number that's slightly bigger than 1, like 1.1, and I put it in here, this is going to produce a number that is a positive small number. Now the numerator, remember, is a negative number. It's -1. So we're taking a negative divided by a positive, which is a negative. And it's getting smaller and smaller on the denominator. So this is going to make a negative infinity limit. Negative infinity. So let's look at some numeric explanation for both of these. So here is my graphing calculator for values for part A, which, remember, the denominator there was quantity 1 minus x squared. I think I said that correctly. Hopefully I did. So when we look at numerically, and here's what I really want you to notice. Do you guys see this 1e to the 6th? That e means it's exponential. In other words, it's 1.0 times 10 to the 6th. In other words, it's 1, 2, 3, 4, 5, 6. So that's a million. So that's a big positive number. Similarly, we got a million on the right-hand side as well. So this is growing without bounds. So we can even see numerically that this is going to positive infinity. If we look at example B on the left, you'll notice that the y value is approaching a big positive number. But on the left-hand side, on the right-hand side, it's approaching a big negative number. So that's why we would conclude that on the left, the limit's infinity, but on the right, the limit is negative infinity. Okay, so let's talk about vertical asymptotes. If it's possible to extend the graph in figure 1.41, the one we did looked at earlier, to positive and negative infinity, we would see that each graph becomes arbitrarily close to the vertical line. This line is called a vertical asymptote. And here's our definition of a vertical asymptote. If f approaches infinity or negative infinity as x approaches c from the right or the left, the line x equals c is a vertical asymptote. So from now on in this class, even though your Algebra 2 or pre-calculus teacher may have taught you different, this is how we define a vertical asymptote. So a vertical asymptote, you could argue, if we go back to, so these are going to produce a vertical asymptote at x equals 1 because the limit goes to infinity. The definition for a vertical asymptote is that the limit at that value of x is infinity. Here's one more piece. This is a theorem about vertical asymptotes, and it's talking about the quotient of a function, and it's basically telling you that if the top function in the numerator is not 0 at the c value, in this case c equals 1, let's say, but the bottom function, the denominator function, is equal to 0, then that's telling us that this is going to produce a vertical asymptote as well. So let's look at our last example here. This is example 2, finding vertical asymptotes. And again, you may already be familiar with, if I gave you a function like this, oh, you just look and you can tell that there's a vertical asymptote at x equals -1. But we can use that last theorem. Would you guys all agree that the numerator function does not equal 0? In fact, it will never be 0. Now look at the denominator function. When will that equal 0? And that's probably what your Algebra 2 teacher or pre-calculus teacher taught you. I guess I should write the conclusion. There's a vertical asymptote at x equals -1 by the theorem on this previous slide, theorem 1.14. Let's look at another example. This one's a little bit more complicated. Here we've got stuff on the top, we've got stuff on the bottom. The first thing I'd like you to notice is the thing on the top, this x squared minus, or x squared plus 1, this is always positive. In other words, it can't be 0. 0 is not positive. It's always positive. What we do need to be concerned about is the denominator. And oops, I guess I kind of wrote over my own thing here. Let's erase everything on the slide. So here we can factor the denominator, as you're probably very familiar with. And so we can see that so when is the denominator going to be 0? Well, that's pretty easy to see. That's going to be equal to 0 when x is equal to 1 or when x is equal to -1. So that tells us the numerator is not 0, but the denominator can be 0 here and here. So that tells us that we have vertical asymptotes at x equals 1. There's also 1, I guess I should say and instead of or, and at x equals -1. So here's that theorem one more time. Theorem 1.14 requires that the value of the numerator be non-zero. It can't be 0. If you end up with a 0 in the numerator, then this theorem does not apply, okay? When both the numerator and the denominator are 0 at x equals c, you obtain what we call an indeterminate form, and we will actually spend a lot more time talking about that when we get into later chapters. Here are some properties of limits based on infinity. These are probably no big surprise. This one's intuitive. If the first limit of f of x is infinity and g of x is L, which is a number, by the way, if I take the limit of their sum, so if I take infinity plus L, I'm going to get infinity. That should make sense. Even if I minus L, that's going to give me infinity. If I take something times infinity, I get infinity, and that's when L is greater than 0. In other words, it's positive. If L is less than 0, it's going to yield -0. That should make sense. This is the one that's probably the most important and maybe the least intuitive. If f of x has an infinite limit, then if I take the quotient of g of x, which is a number not equal to infinity, divided by f of x, that answer is 0. If you take any number divided by infinity, so any number divided by infinity, I guess I should be careful and say not including 0. No, 0 actually works too. Any number divided by infinity is 0. This is a very important result. All right, looks like that's it.